Hello and welcome you all for the today's video. In this video we are going to see the basic concept related to the magnetism. We know that magnet or electromagnet can produce a magnetic field. The field where the magnet attracts or repel magnetic materials such as iron, steel, nickel, cobalt, etc. And as per the electromagnetic perspective, we can define it as a force on moving charge. So this is the formula which has F is equal to Q cross V cross B, where Q is the charge, F is equal to force, V is equal to velocity, or we can say the speed of the particle, and B is nothing but the magnitude of the magnetic field. So this is the first concept. The next is magnetic field strength, which is denoted by the H. The amount of magnetizing force, that means how much force is required to magnetize the magnetic material such as iron, steel, is called as a magnetic field strength, which is denoted by the H. If H is inversely proportional to the length and H is directly proportional to the current, we denote current as I. So from these two formulas we can define the unit of the H, and which is equal to ampere per meter. Okay, so this is the unit of the magnetic field strength. It is a vector quantity. The next concept is a magnetic flux, which is denoted by the phi. In a simple word, magnetic field into the area perpendicular to the magnetic field is called the magnetic flux, which is denoted by the phi. Or it is the amount of magnetic field or magnetic line of forces passing through the surface, like conducting area, space, air, etc. Okay, so we can see here we have the magnetic field which is oriented from N toward the S. Okay, so here I can draw the direction of magnetic field, which is denoted by the B. Okay, it is a vector quantity, so bar must be there, and it has this area. Okay, so I am shadowing this area. Okay, so this is the area which is perpendicular to this field. Okay, if I draw normal to this particular area which is in between the field, okay, so this is normal which is denoted by N. It has same direction as the magnetic field. See, it may be parallel or anti-parallel, so we can see this is N. Okay, so if we want to measure the angle between these two, is 0. Okay, so basic formula for this, as per the definition, the formula for magnetic flux is a magnetic field which is denoted by the B. See, B into A, and this is a cos theta. So why cos theta? I'm going to explain this. See, there is zero angle between these two lines. Okay, because these two lines are parallel, so cos 0 is equal to 1. So this formula ultimately become B cross A. Okay, but what if this surface area has another orientation, like the direction of the normal is like this? Okay, in this case it has a particular angle theta in between them, so it affects the quantity of this magnetic flux. Okay, so that's why this affection is shown by this cos theta. That's why this term has been introduced in the formula, BA cos theta. If the surface is perpendicular to the magnetic field, then it is only the B equal to A, phi is equal to B equal to A. But if surface has some orientation, then we must have to consider the theta, or the angle between the normal and the magnetic field. So this is the magnetic flux. The SI unit of magnetic flux is Weber. I'm drawing Weber, and the formula for finding magnetic flux, this is the formula B into A. Okay, where A is the area in meter square, and we know that CJ's formula for the magnetic flux is a Maxwell. So Weber is a SI unit. This is SI formula. This formula is SI formula, and in CGS formula it is a Maxwell, and instead of Weber we can say Maxwell, in the CGS system, and the formula will become same formula. Phi is equal to A cross B or B cross A, where A is in a centimeter square. Okay, so in the SI unit the area is in meter square, and in the CGS unit area is in centimeter square. Okay, so this is the difference between SI and CGS. Then next concept is magnetization. This state of material being magnetized, or the process in which magnetic material is magnetized. It is nothing but the magnetization, and it is denoted by the M, capital M. Okay, so it is the density of permanent magnet or the electromagnet dipole moment in a magnetic material. Or we can say that the magnetic moment, that is which is denoted by small m. See, here is the total magnetic moment denoted by small m, and this is volume is in meter cube. Okay, so another definition of this magnetization is nothing but the ratio of total magnetic moment to the volume per unit volume, which the volume is in meter cube. Okay, so this is the another definition, and from this definition we can define the formula, which is m is equal to small m divided by v. We have to note that the small m is a magnetic moment, and capital M is nothing but the magnetization. Okay, so this is the magnetization. It is again a vector quantity, and yes, it is a vector quantity. The next is magnetic permeability. Okay, so what does it mean, the permeability? If we break this word, the permeability, if we break this word permeability, per means permission, and ability is nothing but the feature or skills to do something, or we can say skills to something. Okay, so if we combine these two words, the permission and the skills to do something, the word formed as a permeability. So permeability is nothing but the ability of material, that how does it easily magnetize. So that is what the magnetic permeability is. So in this video we are going to consider the magnetic permeability of the vacuum, which is a standard. Okay, so magnetic permeability of vacuum is nothing but the amount of resistance encountered to the magnetic field when it is forming into the vacuum. Okay, so this is nothing but the resistance which for the formation of the magnetic field when it is forming into the vacuum. So the SI unit of permeability is H by M. See, we can see here H by M is the SI unit of the magnetic permeability. And also it has the another form in the Newton per ampere square. See, N per ampere square. This is the another we can convert this unit. Okay, and see, we can see mu 0. This is denoted by mu 0. Okay, this is the notation of magnetic permeability in a vacuum. If it is in a vacuum, then 0 must be there, or we can say mu naught. Okay, so the value of mu naught is 4 pi into 10 raised to minus 7, and if we calculate it, it has an approximate value of this much, 1.2566370614 H per m. Okay, see, H per m, or we can say N by A square. Okay, respectively. So in this is SI, this thing is in SI. The CGS unit of magnetic permeability in a vacuum is 1. Okay, it has one value. Then next is magnetic susceptibility. We know that in electromagnetism, the magnetic susceptibility. So what that susceptibility means? Susceptibility is nothing but the receptive, and which is denoted by the chi. See, this is a symbol for susceptibility. It is a measure of how much material will become magnetized in the applied magnetic field. So it is what the susceptibility. Okay, I repeat, it is a measure of how much material will become magnetized if it is into the applied magnetic field. Okay, so it is nothing but the ratio of magnetization M to the applied magnetic field intensity H. So susceptibility, we can see here, susceptibility is nothing but the magnetization to the H. So this is the formula for susceptibility. Okay, so why this concept is important in magnetism? So this concept allows us the simple classification to the two categories, that is most material responses to the applied magnetic field, which has that means the alignment of the magnetic dipole according to the magnetic field, where the susceptibility is positive, which is called as a paramagnetism. So this is the condition. Okay, so this is the condition for the paramagnetism. If your susceptibility is positive, then the substance is or material is paramagnetic material, and if it is negative, it will be diamagnetic. Okay, so we can easily classify the materials into the paramagnetic and diamagnetic materials by using this concept. So that's why this concept is very important. So thank you so much